in this problem, I'm going to consider two blocks, one of mass 1, one of mass 2, one of which is sitting on an inclined plane attached to the other by a massless string over a massless pulley. In this situation, the acceleration of both blocks will be 0. So our system is going to be in equilibrium. And hopefully, you're already at the point where this is triggering the thought, oh, net force equals 0. I know that the block of mass 2 in this problem is 10 kilograms. And we're also going to have the angle of incline for our inclined plane be 41 degrees. I want to know what is mass 1. In fact, this system that we're going to work out the mass of block 1 for is a very rudimentary scale. So you could figure out the mass of something that you don't know using the mass of something you do know, a string and an inclined plane. This thought that acceleration is 0 and therefore net force is 0 is going to be the ultimate way to solve the problem. So I'm interested in block 1. Let's look at the forces on block 1. So if I draw a free body diagram for block 1, there is a force of gravity down, and there is a tension force from the string pulling up. Now, because this system is in equilibrium, these are both y forces, positive y, negative y, I know that Ft equals Fg. So if I could find the tension force, I would have found the gravitational force, and because I know that Fg is mg, if I find the gravitational force, I could easily find the mass of block 1. So just to be clear, block 1, block 1, block 1. And you might think, oh, well, don't you need to number the tension force? Shouldn't that be the force of tension on block 1? No. For this, we're going to appeal to the Bob Marley rule of one string, one tension. So that tension describes an internal force happening in that rope. It also describes the force of the rope on the blocks at both ends. But because there's only one string, it can only support transferring that one internal tension. So one string, one tension. And it's not formally called the Bob Marley rule, that's just a joke. You should Google it. That means if I can find the tension force that's holding up block 2, I would have also found the tension force holding up block 1. So let's consider that. I'm now looking at something on an inclined plane. And whenever you have something on an inclined plane, there's a problem-solving trick. Take the standard XY coordinate system and rotate it so that X lines up with your inclined plane. See here, I'm going to rotate it so that X lines up with the inclined plane. Let's draw that new coordinate system with the block 2 at its origin. So this will be positive Y, this will be positive X, this will be negative X, and this will be negative Y. And now I'm interested in the tension here. Tension. So we should probably also consider the other forces on this block. Well, there's the normal force that points at 90 degrees. And handily, notice that that now lines up with the positive y-axis. Gravity, though, still has to pull straight down. Not allowed to pull any other way. And because I rotated this system so that X lines up with the inclined plane, that means the whole coordinate system was shifted by 41 degrees. So I know what used to be negative y and what is now negative y have 41 degrees between them. Now again, we're going to use this system in equilibrium, net forces equal 0. Because of the way that I have cleverly lined up my coordinate system, this tension is a negative x force. And if the system is in equilibrium, there is an equal positive x force. Now the only vector here that has an x component is gravity. In fact, it would be this component right here. And by the rules of trig, that's opposite my angle. So the FG2 x component in this new coordinate system would have to be the force of gravity on block 2 times opposite that trig function is sine 41 degrees. That FG2x has to be equal to the force of tension, because remember, tension is an x force. FG2 sine 41 degrees is also an x force. These are the only two forces in x up here. And so the negative x1 has to equal the positive x1 so that I can have a total F net in x of 0. Now if I keep on thinking about this, that means that this whole thing is also equal to the force of gravity on block 1. So I can go ahead and write FG1 equals FG2 sine 41 degrees. And then we discussed that that's just M1 times G. So M1G equals FG2 sine 41 degrees. Well, what's FG2? It's the mass of block 2 times little g. So M1G equals M2G sine 41 degrees. Handily, the g's cancel. And now I have M1 equals M2 sine 41 degrees. And if I substitute in the mass of block 1, which was 10 kilograms, this is 10 kilograms sine 41 degrees. And if I grab a calculator and multiply that out, I get that block 1 is 6.56 kilograms.